All right, hello everyone. Welcome back to GISC 1336, Digital Drafting and Design. Today, we begin Lecture 6, where we shift our attention to the topic of site surveys. At first glance, site surveys might look like a cousin of the boundary survey. Both involve field crews collecting data, both involve drafters processing that data in Civil 3D, and both result in drawings that carry professional significance. But the purpose, the audience, and even the consequences of the two are not the same. To understand where we are heading with site surveys, we must look briefly backwards. In Lecture 5, we studied boundary surveys in depth. We talked about how the goal of a boundary survey is to retrace the footsteps of the original surveyor. We saw how courts in Texas, through cases like Stafford v. King and State v. Post, reinforced the principle that boundaries are not inventions of new math, but legal realities tied to monuments, deeds, and history. We reminded ourselves that the footsteps of the surveyor upon the ground should always be followed. In other words, boundary surveys are legal in nature. They're about ownership, history, and evidence. They look backwards to confirm what has already been granted, conveyed, or occupied. A site survey, however, looks in the opposite direction. Instead of being rooted in past evidence, it is oriented towards future use. The site survey is the survey of development. Its audience is not the court, but the engineer, the architect, the planner, or the contractor. Its purpose is not to settle disputes over ownership, but to provide an accurate, reliable, and detailed picture of what exists today, so that new work can be designed and constructed tomorrow. If the boundary survey is the historian of the land, the site survey is the engineer's scout. Now, this doesn't mean that the site survey is less important or less rigorous. It simply means it's framed by a different question. Where a boundary survey asks, what are the legal limits of this property? The site survey asks, what is on this property and how will those features affect design and construction? The drafter then must adjust their mindset accordingly. One way to think about it is like this. Boundary survey guards the rights of ownership, while the site survey enables the work of improvement. The boundary survey protects the past, while the site survey prepares for the future. Both rely on accuracy, consistency, and fidelity to evidence. Both require careful drafting, but the evidence you are representing is different. And because of that, the consequences of mistakes are also different. If you make an error in boundary survey, you may misrepresent ownership, leading to disputes or even lawsuits. If you make an error in a site survey, you may cause a building to be designed in the wrong place, a drainage system to fail, or a utility line to be cut during construction. In either case, the damage can be significant. So as we begin Lecture 6, I want you to keep this comparison in mind. Site surveys and boundary surveys share tools and methods, but they diverge in purpose. One is backwards looking, grounded in history and law. The other is forward looking, grounded in present conditions and future planning. As we move through this lecture, we'll see how site surveys are defined, how they are conducted, and how the drafter possesses and presents the data, and how the responsibilities we learned in earlier lectures continue to apply, though with a different focus. And I'll keep coming back to our course's guiding principle. Every line you draw is either helping or hurting the surveyor's certification. That does not change whether you are drafting a plat to protect a deed line or drafting a site survey to support a subdivision design. In both cases, you are shaping the professional integrity of the surveyor and the trustworthiness of the record. Now that we've set the stage by contrasting boundary and site surveys and their purpose, let us dig deeper into what a site survey actually is. When I say site survey, I'm talking about the detailed mapping of the physical features, the topography, and the improvements that exist on a given tract of land. Unlike a boundary survey, which starts with the deed, the patents, and the historical record, a site survey starts with the here and now. Its mission is to capture, as completely as possible, what is on the ground today. The client is not asking us to solve a boundary dispute or reestablish a lost corner. The client is asking us to prepare a reliable base upon which design and construction decisions can be made. So, who is the audience for a site survey? Most often, it is engineers and architects. They need to know the slope of the land before they design a subdivision. They need to know where the existing water lines and sanitary sewer mains are before they plan a new commercial development. They need to know where trees stand, where ditches drain, and where easements cut across, and where the pavement edges lie. Sometimes the audience is a city or a county permitting office that requires a current site survey before approving development plans. Other times, the audience may be a contractor who needs the survey for staking and layout. The key is that the audience is forward looking. They're trying to change the land, and they need the drafter's drawing to be the truth upon which they can safely build. So let's talk about the components. A site survey typically includes topography, improvements, vegetation, utility, and drainage, and each one deserves attention. Topography is often the backbone. Field crews will take shots across the property, locating elevations at key points. Break lines are gathered at ridges, swales, curbs, and ditches. Those points, once imported into Civil 3D, form a surface, and from that surface, contours are drawn. Remember what we said back in Lecture 3. Contours are not just lines on a map. They're the language by which we communicate the shape of the ground. And that lesson applies directly here. For an engineer designing a parking lot and a drainage plan, or a building pad, those contours are the basis for every decision. If they are wrong, the design will be wrong. Next, we have improvements. A site survey must document every improvement with accuracy. Buildings, driveways, sidewalks, fences, retaining walls, curbs, parking lots. All of these must be captured. The footprint of a building must be drafted as a closed figure. Driveways and sidewalks must be tied into the survey control. A fence line that appears in the field must appear on the drawing, even if it is old or in poor condition. Remember, you are not designing in this phase. You are representing reality. Vegetation can also be important. Many municipalities in Texas have ordinances that protect heritage trees. And these are trees of a certain species and trunk diameter, often live oaks, pecans, or cypress. Removing them requires permission, and designing around them may be necessary. And this is why site surveys often note tree species and trunk diameters. If you omit a line, you may cause the designer to propose a plan that later gets rejected by the city. The responsibility for accuracy rests with you. Utilities are perhaps the trickiest part. A site survey must capture visible utility features. Manholes, fire hydrants, valve boxes, utility poles, pedestals, and meters. In addition to these, it must show underground utilities as marked by a locate service. This means you may be drafting based on paint marks, flags, or local reports provided by third parties. The challenge here is clarity. You must use consistent symbols and labels so that anyone reading the drawing understands what utilities are present. Confusion can cause expensive mistakes during construction. And drainage is another critical component, especially in Texas. Our rainfall can be intense, and our soils can complicate how water moves. A site survey must show ditches, culverts, inlets, head walls, swales, and other drainage features. If a tract is in a FEMA floodplain, that must be noted. If a culvert crosses a road, it must be drafted in its correct position. Why? Because the engineer designing stormwater management will rely on that information completely. A missed culvert can change the entire drainage plan. Now, beyond these general components, there are also different types of site surveys that you may encounter in your careers. A topographic survey is perhaps the most common, focusing on elevations, contours, and break lines for use in grading and drainage design. An as-built survey occurs after construction is complete, verifying that improvements were built as designed and serving as a permanent record for permitting or warranty. A utility service concentrates on locating above ground and underground utilities so that designs can avoid conflicts. And a tree survey documents trees in detail, especially heritage trees, protected by ordinance. And a floodplain survey ties elevations to FEMA benchmarks, providing critical information about whether improvements will be impacted by base flood elevations. All of these fall under the umbrella of site surveys, but each has its own scope and audience. And I want to give you a simple way to remember this. The boundary survey asks, where is the line? The site survey asks, what is on the site? Both questions are important, and both require evidence, but the evidence they seek is different by nature. And let's also consider the consequences of error. If a boundary survey misplaces a line, two landowners may end up in court, fighting over property rights. If a site survey misrepresents the ground, a building might be designed in the wrong place, or a drainage system may fail, or a contractor might cut into a utility line. Both situations can lead to financial loss, liability, and professional embarrassment. And that is why fidelity to evidence is just as important here as it was in Lecture 5. And finally, we must remember the board. Even though the site survey is for design and not for resolve and ownership, it still falls under the same professional rules. It must be signed and sealed by a licensed surveyor. That means every feature you draft, every contour, every utility, every building footprint carries the same weight of responsibility as a boundary line in a plat. The context may be different, but the professional duty is the same. So, to define the site survey, it is the comprehensive mapping of existing conditions intended to support design, planning, and construction. It includes topography, improvements, vegetation, utilities, and drainage. It differs from boundary surveys in purpose, audience, and scope, but it shares with boundary surveys the same demand for accuracy, consistency, and fidelity to evidence. A site survey does not begin with a deed or a courthouse search the way a boundary survey does. It begins with the scope of work, usually written by the client or by the engineer who is planning a design project. The scope of work may say something like this. Provide a topographic and improvement survey of the tract located at 123 Main Street. Show all existing buildings, utilities, drainage features, and vegetation. Provide contours at 1 foot intervals tied to NAVD 88 elevations and horizontal control tied to Texas State Plane coordinates. In that sentence, the client has already told us the purpose and the expectations. This is not a resurvey to confirm title. This is a current condition survey to support engineering and design. And here is where communication becomes essential. A good drafter remembers that every survey starts with dialogue between the client and the surveyor. That conversation defines not only the technical scope, what features must be shown and to what accuracy, but also the deliverables. Will the client require a DWG file, a PDF exhibit, a signed hard copy? Must the drawing be tied into state plane coordinates or into a local grid? Should elevations be NAVD 88 or is another vertical datum preferable? If these questions are not clarified up front, misunderstandings can occur. The drafter must be aware of these expectations because they shape how the survey is processed, drafted, and delivered. And once that scope is understood, the surveyor begins planning for the fieldwork. Control will be established first. A GPS base station may be set, or real-time corrections may be received from a network. Known benchmarks are recovered, or new benchmarks can be set. In Texas, this often means tying into local monuments set by TxDOT or by city public works departments. And control matters because every point the crew collects must be tied into a consistent system so that distances and elevations are meaningful across design. And then comes the fieldwork of locating features, using total stations, GPS rovers, or even both that collect points across our sites. Each point is recorded with coordinates, elevation, and a description code. These codes are what allow the drafter back in the office to build the drawing correctly. If a point is taken at the edge of pavement, it might be coded EP. If it is a tree, it might be TR with a diameter noted. If it is a manhole, it might be MH. These codes, applied consistently, preserve the link between what the crew saw and what the drafter will show. This process is often referred to as field to finish, and we introduced it back in Lecture 3 when we discussed surfaces. The idea is simple but powerful. The data collected in the field flows directly into the drafting environment, producing line work and symbols automatically. The drafter is then refining, checking, and clarifying, not inventing from scratch. This is where our chain of custody of evidence becomes so important. Every code, every point, and every shot is part of our record. And it's our job as the drafter to preserve it faithfully. In Texas, well, it adds its own challenges to field procedures. In some areas, expansive clays cause the ground to shift seasonally. In other areas, like the Gulf Coast, standing water and soft soils make GPS work more difficult. In urban areas, dense utility corridors create clutter that must be carefully located. In rural South Texas, brush and mesquite can make line of sight difficult for total stations. Each region imposes its own field challenges, and the drafter must remember that the data arriving in the office is the product of these real-world conditions. Another important aspect of site surveys is the location of underground utilities. While visible features can be located directly, underground utilities often require coordination with one-call locate services, things like 811. And crews may rely on paint markings or flags to record approximate locations of water, sewer, gas, electric, or telecom lines. These are then plotted by the drafter, usually with a note that they are based on locates and not on excavation. This distinction is critical. It communicates to the engineer and contractor that these utilities are believed to exist, but their exact depth and alignment may vary. And once the data comes back to the office, the field book, or more often these days, the data collector file, will be downloaded. The points reviewed. If the crew noted unusual conditions, a culvert partially blocked, a fence offset from a property line, a tree that was dead or dying, those notes must be carried forward. As the drafter, you must not only process these codes, but also interpret the notes from the field crews. If you see that a manhole was flagged as covered or inaccessible, you must show it accurately with that notation. If you omit it, you may mislead your target audience. your clients. And this is where the professionalism of the drafter shines through. Anyone can import points into Civil 3D, but not everyone can think critically about what those points mean. You must connect the dots, literally and figuratively. You must ensure that the line work represents reality, and you must check that surfaces make sense. You must question anomalies, ask the surveyor for clarification, and resolve inconsistencies. The consequences of neglect can be severe, and if deliverables are not prepared correctly, the CAD file does not match the plotted sheet, if the vertical datum is inconsistent or erroneous, if our coordinate system is just flat wrong, the engineer or architect may discover far too late that designs are misaligned. And this is why communication with the client and clarity in deliverables are every bit as important as the field data itself. And I will repeat the guiding line one more time for y'all. Every line you draw is either helping or hurting the surveyor's certification. Every omitted tree, every miscoded ditch, every mislabeled manhole, and every misplaced file coordinate is either preserving the truth of the site or eroding the trust placed in the survey and the surveyor. That trust is the foundation upon which engineers and architects will hold us. Once our field data reaches the office, the drafter takes center stage. The field crews collected thousands of points, coded them carefully, and documented conditions. But raw data is not enough. Someone has to transform those points into a coherent drawing, a drawing that an engineer, an architect, or a contractor can trust. And that task falls to the drafter. When you build a surface in Civil 3D from field data, you're creating more than just lines on a page. You're creating a model of the land itself. And from this model, contours are generated, and those contours are the language of the ground. Engineers read them to design drainage, grading, and foundations. If the surface is wrong, every design decision that follows will be compromised. This is why you must think critically about the surface. Do the contours make sense? Do they show water flowing downhill? Or have you accidentally created impossible flow directions? Line work follows the same rules. When edge of pavement shots are coded in the field, they should connect into a clean line in your drawing. When a fence is shot, it should appear as a continuous feature. When buildings are drafted, they should close into complete shapes. These may sound like small details, but they are not. They are the very things that make the difference between a drawing and a professional, and one that is sloppy. Now, let's talk about quality control and professional responsibility. In Lecture 2, we said that the drafter is the final line of defense before errors become permanent. That is no less true here. Once you have built your surface, drafted your line work, and applied your styles, you must review every detail. Do the contours close properly? Are the elevations consistent? Are utilities labeled? Are there any gaps or overlaps in our line work? And here's where the legal and ethical considerations come in. A site survey may not be resolving ownership, but is still a professional product sealed by a licensed surveyor. That seal carries liability. If a building pad is designed in the wrong place because you omitted a drainage ditch, the consequences will be real. Board rules require accuracy, clarity, and consistency, regardless of survey type. That means ethical responsibility is not limited to boundary surveys. It extends to site surveys as well. You are drafting a legal record, and the surveyor is staking their license on your work. And the principle is simple. Software can automate many tasks, but judgment and responsibility will always belong to you. Civil 3D cannot tell you whether a symbol means the same thing on every sheet. It cannot tell you whether a tree is significant under local ordinance. And it cannot tell you whether a utility line makes sense in the context it's shown. Only the drafter can do this. And if you fail, the liability is not erased because that's how the software drew it. The board will hold the surveyor accountable, and the surveyor will have relied upon your work. So remember, every line you draw is either helping or hurting the surveyor's certification. And in Civil 3D, those lines may be generated automatically, but they are still your responsibility. Now, it is also important to understand that site surveys often serve as a bridge to construction staking and land development. Once the site survey has been drafted and engineers have prepared designs, the next step is often to take those designs back into the field. Construction staking uses the design drawings to physically mark where buildings, roads, and utilities will be built. If the site survey was wrong, the staking will be wrong, and the construction will follow. This link reminds us that accuracy in site surveys is not just about drafting a clean drawing. It is about enabling the next phase of real-world work. Think about this chain. Boundary surveys establish ownership. Site surveys capture conditions. Construction staking translates designs into physical marks, and construction builds upon those marks. Each link depends on the integrity of the one before it. If you, as the drafter, weaken the link at the site survey stage, everything that follows will be compromised. So let's compare again. Boundary surveys are rooted in history. They are governed by deeds, monuments, and the hierarchy of evidence we discussed in Lecture 5. Their audience is often a court or landowners in dispute. Site surveys, on the other hand, are rooted in present reality. They're governed by accuracy of topography, improvements, and utilities. And their audience is engineers, architects, and contractors. The hierarchy of evidence is not legal precedence, but a physical completeness. And then we look forward to plats. A plat formalizes the work of both boundary and site surveys into a legal record, subdividing land, dedicating right-of-ways, and creating lots. A plat is both legal and physical. It depends on the boundary of the survey to define limits, and it depends on the site survey to show improvements and conditions. Together, boundary surveys and site surveys and their plats all converge into a broader picture of land development. Now, finally, we extend our view further ahead to the ALTA or the NSPS land title surveys, which we will study in a later lecture. These surveys combine all of those elements, boundary retracement, site conditions, and legal dedications, into one comprehensive standard designed for lenders, title companies, and attorneys. ALTA surveys, they show boundaries like a boundary survey, improvements like a site survey, and easements of right-of-ways like a plat. They represent the culmination of the progression we have been building in this course. So you can see the trajectory clearly. Our boundary surveys look backwards. Our site surveys look at the present. Our plats formalize ownership and use in legal records. ALTA surveys unify all of these into one standard product. Each step builds upon the one before it, and as a drafter, your responsibility is to be competent in each step, to know the differences, and to preserve accuracy and trust at every stage. And I want to underline this point one final time. Every line you draw is either helping or hurting the surveyor's certification. In a boundary survey, that line might represent a deed call. In a site survey, it might represent a contour or a utility. In a plat, it might represent a lot line or an easement. And in an ALTA survey, it might represent all of the above. The principle never changes. As we bring Lecture 6 to a close, I want to step back and make sure you see the bigger picture. We began today by contrasting site surveys with boundary surveys. We remind ourselves that boundary surveys are about the past. They are legal in nature, rooted in deeds, monuments, and the hierarchy of evidence established by Texas courts. They retrace footsteps, confirm ownership, and protect rights. By contrast, site surveys are about the present. They capture the physical reality of a tract of land in its current state. Its topography, its improvements, its vegetation, its utilities, and its drainage. Their audience is not the court, but the engineer, the architect, the planner, the contractor. They are forward-looking, laying the foundations for design, permitting, and construction. Where boundary surveys guard ownership, site surveys enable progress. Along the way, we examined the details of what site surveys include. We talked about contours as the language of the ground, about improvements that must be drafted as complete and accurate figures, about trees that may be protected by ordinance and utilities that may be depicted clearly, and about drainage features that dictate how water moves across the land. Each of these components is part of the responsibility of the drafter, because each one has real consequences in design and construction. We also added that site surveys may take specialized forms: topographic, as-built, utility tree, or floodplain surveys, each tailored to a specific purpose, but united by the same standard of accuracy. We then turned to field procedures. We saw how scope of work defines the mission, how crews use GPS and total stations to collect thousands of points, and how coding preserves the link between what was observed in the field and what is drafted in the office. We recognize that Texas adds its own challenges: expansive soils, floodplains, dense urban utilities, and that the drafter must interpret data with awareness of these realities. We emphasize that communication with the client is critical, because the scope defines not just the technical features to be shown, but also the deliverables. State plane coordinates, vertical datums, elevations, DWG PDF files, everything that engineers, architects, and permitting agencies depend upon. From there, we discussed drafting and civil 3D workflows, but not as a technical manual. We spoke of surfaces as models of the land, point groups and description keys as tools of consistency, line work as the expression of reality. We briefly touched indirectly on external references as the foundation for entire design sets. We emphasize that the software serves the drafter's judgment, not the other way around. And we reinforce that the board still holds surveyors accountable for accuracy, meaning that ethical responsibility and liability are carried in every site survey, just as they are in a boundary. Finally, we return to comparisons. Boundary surveys look backwards. Site surveys look forward. Plats formalize conditions into legal records. ALTA surveys combine them all into one comprehensive standard. Construction staking bridges site surveys into the world of construction. And as a drafter, you must be able to navigate all of these phases, understanding the difference, but applying the same professional discipline to each one. So what do we carry away from Lecture 6? We carry the recognition that the drafter's responsibilities, accuracy, consistency, communication, legal awareness, and quality control, do not change from one survey type to another. What changes is the kind of evidence you represent and the audience you serve. Whether you're retracing a deed line, drafting a plat for recording, or mapping improvements for design, your fidelity to evidence and your clarity in drafting remain essential. I want to close with the same guiding phrase we have repeated throughout this course. Every line you draw is either helping or hurting the surveyor's certification. In a boundary survey, that line may represent a deed call traced to an ancient monument. In a site survey, that line may represent a contour guiding a drainage design. In a plat, that line may define a lot that will house a family for generation. And in an ALTA survey, that line may reassure a lender investing millions of dollars. In every case, the line matters. And that is why we study not only the tools, but the principles and how they're used. That is why we tie every lecture back to the larger arc of professional surveying in the state of Texas. And that is why we emphasize that drafting is not just a drawing, but a professional responsibility that shapes the trustworthiness of the entire record. So as you prepare for the next stage of this course, remember that site surveys are not just technical products. They are bridges between the land as it is and the land as it will be. They are the drafter's contribution to progress, development, and public welfare. And with that, we conclude Lecture 6. Thank y'all.